Today's lecture is on systems of equations. I know it's been a long time since we've talked about systems of equations. The last time we discussed them, we were mostly looking at graphs, right? We were in Module 1 when we were mostly looking at visual representations of the things we were talking about. So let's refresh a little bit on that. So if you'll recall, we had three situations with linear systems. We're only going to be working with linear systems in this lesson. We had this first type of linear system where we had one solution, right? They intersected once and the solution was the intersection. We had the case where we had parallel lines when there was no solution. And we had the case that, again, is sort of hard to draw. The best I can do is make sort of a thicker than normal line where we have overlapping lines, right? Two of the same line. And in this case, we had infinitely many solutions. So, like we've done with a whole bunch of other topics this semester, we are going to move from just looking at it in the graphical sense and moving it towards the symbolic and algebraic sense. So, the way we can represent systems in an algebraic way or symbolic way is like this. They kind of are multiple equations grouped together, usually with the same variable showing up. For example, perhaps you're looking at something like this. So this is a system of three equations, and we have three variables involved. But for example, this second equation doesn't have a z. That's totally fine, right? It just means that that z has a coefficient of 0. Similarly, this third equation is missing a y. That's also okay. We just have a coefficient of 0 on that y. In this class, we're mostly only going to be working with systems of equations where we have two equations with two variables or three equations with three variables. We won't see things outside of that, although that does exist and is what you would be working on if you go on to linear algebra. Let's talk about solving systems in two variables. There are multiple ways we can do this. The first way is what's known as substitution. And for this, we're going to turn to our lab manual. Okay, so our lab manual gives us steps for the substitution method. So let's go ahead and use them to work on this one as we go through. So the first step is to solve one equation for one variable. So if I look at these two equations, what variable of these four terms is going to be the easiest to solve for? Probably this x, right? Because it's already got a coefficient of 1. So let's go ahead and solve there. So this is step 1. So we've got x minus y equals 8. We can move that y over. We end up with x equals y plus 8. So that's our first step done. Our second step tells us to substitute the expression, so this, into the other equation for the variable you solved for, so for x, to create an equation with just one variable. We've done this before, haven't we? We've done this in polynomial modeling. We've seen this before in polynomial modeling. So this actually, hopefully, feels a little bit familiar. So step 2, we're substituting this into our second equation for x. So I'll go ahead and rewrite the whole thing over here. And then we're plugging in for x. So we've got 4 times y plus 8 minus 2y equals 20. Solve the resulting equation to determine the value of one of the variables. So we want to solve this. We can distribute here. We've got 4y plus 32 minus 2y is 20. Let's bring this 32 over and combine these guys. So we end up with 2y equals 20 minus 32, which is negative 12. So y is 6. Great. Last step. Substitute the found value back into the equation to determine the value of the second variable. This is, again, just like what we did in polynomial modeling. So hopefully this feels familiar. So substitute y equals 6 back into either equation, right? It doesn't tell us which one we have to plug into to determine the value of the second variable. Just like we did with polynomial modeling, we've already got what x is in terms of y. So we can plug in for y here and just get x right out. So we know that x equals y plus 8. So x equals 6 plus 8. So x equals 14. This is my answer. In WebAssign, you're often asked to give the solution in this form, so as x and y. So here, that would just look like 14, 6. Great, okay, let's do a couple other examples. All right, is there something easy for us to solve for here? Yeah, let's solve for x again. So x minus y equals 1. That gives us x equals y plus 1. Awesome. So we can plug this into the other equation. We have to plug it into the other equation. If we plug it back into the same equation, it's just going to give us something like 1 equals 1. Nothing interesting. We need interesting stuff, right? So we want to plug y in for x in this second equation. So we have y plus 2y, so 3y. And then let's bring this 1 to the other side, so 3. So we end up with y equals 1. We know that x equals y plus 1. So x equals 1 plus 1, or x equals 2. And to put this solution in the way that we recognize, or that WebAssign will recognize, we can just write it as xy equals x, or 2, y, 1. One more real quick. Let's say we're looking at x plus y equals 2. And 2x plus y equals 3. let's solve for something. This time, let's solve for y, just cause, right? We have y with a coefficient of 1. So let's go ahead and just solve for y, because why not? So let's bring x over, and we end up with y equals 2 minus x. We can plug that into our second equation. So we get 2x plus y is 2 minus x. All this equals 3. Oh no. And again, this is coming from 2x plus y equals 3. We combine like terms. So we have 2x minus x. That gives me just x. And then this 2 over here, we want to bring that 2 over here, so we end up with 1. And I can plug this 1 right back into this y equals 2 minus x, and I end up with 2 minus 1, so y equals 1. My final answer being x, y equals 1, 1. Great, let's go ahead and talk about the second method. So method 2 is called elimination. This is also in the lab manual, so let's turn to that page. Let's take a look at this first one here and follow the steps that it gives us. So the first step is to organize the system with all variables on one side and the constant on the other side. We want to make sure that the variables in both equations are in the same positions. So here we have that, right? We have them sort of lined up. We have the terms with variables on one side, and we have the constant term on the other side. And the x's are in the same positions and the y's are in the same positions. So we're all lined up. So this is done. Second step is to use a multiplier or multiple multipliers to create equal coefficients with opposite signs. Equal coefficients with opposite signs. I'm going to underline that. For one of the variables in the system. So which of those here is going to be the easiest to do? Well, we've got 3x and 2x. In order for these to become equal coefficients with opposite signs, we'd have to get them to the least common multiple, which is 6, which means we'd have to multiply this equation by 2 and this equation by 3, or negative 3, right? Because we want it to have opposite signs. That's a lot of work. Let's see if y is any easier. So we have 4y here, and we have negative y here. What would we have to multiply this equation by to have an equal coefficient with an opposite sign? Just by 4, right? Very simple. If we multiply this whole equation by 4, then we'll have a coefficient here of negative 4y and here of positive 4y. So that's equal coefficients with opposite signs. So let's do that. So times 4. So we've got 3x plus 4y equals 5. We multiply the whole second equation by 4. We get 8x minus 4y equals negative 38. So we've got equal and opposite signs. Add the equations together and eliminate one of the variables. Okay, so adding these equations together, kind of like we were doing with long division, polynomial long division, we end up getting 3x plus 8x, which is 11x. 4y minus 4y. Do y'all see why it was important for us to have equal but opposite sign coefficients? Yeah, when we're adding these equations together, this is 0, right? So we can sort of leave a space there. And then 5 plus negative 38 gives me negative 33. So that's step 3. Step 4 is to solve for the value of the remaining variable. So we have 11x equals negative 33. If we divide by 11, that gives us x equals negative 3. This is asking us, last step here is to substitute the found value, so this guy, back into an equation to determine the value of the second variable. We can plug it in to either. I'm going to plug it into the first one because it doesn't have any decimals. 3x plus 4y equals 5. So we have 3 times negative 3 plus 4y equals 5. So negative 9. We bring that 9 over. We end up with 4y equals 16. So y equals 4. So my solution here is xy equals negative 3, 4. Awesome. Let's do another. All right, looking at number 3 now. So I want to get, again, equal but opposite signs here. What can I do? Well, if I look at x, we want equal but opposite signs. It would make more sense for us to multiply this smaller equation to get to this larger number. What can I multiply positive 2 by to become negative 4? Negative 2, right? Negative 2 times negative 2. So we have negative 4x plus 12y equals negative 18. We bring this one over. We've got 4x minus 12y equals 27. We add these guys up. These guys cancel, which is great. What happens when I add these guys? They also cancel. So these guys have canceled as well. So on this whole side of the equation, I've got 0 plus 0, or 0, right? Over here, I've got negative 18 plus 27. That gives me 9. So what I've gotten when I added these together is 0 equals 9. Is this a true statement? No, this is false. This is a false statement. What does it mean if we get a false statement trying to solve these two equations? Well, it means that there's no solution. That makes sense, right? If I try solving these equations and I get a false statement, it means that no x and y pair are going to be able to plug in here to make this work out. No matter what, it's going to give you something turns out to be false. So, no solution. This puts us in the case we were talking about when we had parallel lines. And that sort of makes sense, right? Because we have these same sort of coefficients here that would help us determine the slope of the line. But they have different constants, right? So the things that would help us determine their y-intercept. Because these are the same, but these are different, we have a false statement, so no solution. Okay, let's try one more. Okay, so this last one, we've got to do a little bit to make it look normal, or to make it look the way we want it to look. So let's go ahead and rearrange these in the way that we would like. So 3x, we want to bring all of the variables over to the left side so that the constant is by itself. So let's bring that 4y over. And then this guy's good to go, so we can just write that underneath. Okay, so let's go ahead and get that equal coefficient with an opposite sign. Looks like this first term here is pretty easily set up for us to kind of match up with this guy, right? We could just multiply by -3. So we've got 3x minus 4y equals 12. We end up with -3x plus 4y equals -12. We add these together. We look at this column. These guys are good, right? We've eliminated x. We look at this second column. What's up? We've again got that case where we've eliminated both variables on the left side. So we have 0 here. What's up with this constant column? We add 12 plus -12. We also have 0 over here. 0 equals 0. Is that true? Yes, this is a true statement. What does it mean if we have a true statement? Well, it means that we have infinitely many solutions. It means that these lines are the same line. But that doesn't mean that we can just plug in any pair x and y and get true statements for both of these, right? We have some restrictions that we need to look for. So how can we figure out what those restrictions are? Well, let's look at this next part. So the final answer can be written in the following way, and then it has this kind of confusing thing, but all it means is that we have a bunch of points, right? Point x, y, where x is equal to some function of y, right? X is in terms of y for any real number y. And so what this is saying is, in other words, x can be expressed in terms of y. So let's figure out what x is in terms of y. We know that x minus 4/3y equals 4, which would mean that x equals 4/3 y plus 4. This is x in terms of y. So we know that our final answer can be written as xy equals, we want y to be whatever, right? Y can be anything. And we want x to be 4/3 y plus 4. Now, what does this mean? I know I don't have a ton of extra room here, but I'm going to do sort of an example down here. What this means is that if I pick any y value, then a point that's going to be a solution to this system of equations is going to have this structure. So for instance, let's pick y equals 6, for example. If y is 6, then x is going to be 4/3 y plus 4. In this case, 4/3 times 6 plus 4. 4/3 times 6 is 8. This is 8 plus 4, or 12. So that means that the point 12, 6 is a solution. It would be better to say 12, 6 is one of many solutions. So that's what this means. All right, let's look at a couple more examples of this. Example 1, let's say we have -2x plus 3y equals -1. and 3x minus 4y equals 2. We've got to get equal coefficients with opposite signs. If we wanted to multiply one of them by something, for instance, multiplying the smaller one up to the larger one, we'd have to multiply this equation by 3 over 2, right, by 1.5. That doesn't sound necessarily nice to work with. So what I'm going to do instead is, we know that the least common multiple here is 6, right? The smallest number that has a factor of 2 and 3 is 6. We also know that this x value is negative and this x value is positive, right? So they're already opposite signs. So let's try and get them to positive and negative 6. So what could I multiply by this guy to make it negative 6? Just 3, right? Times 3. So I multiply this times 3, I get negative 6x plus 9y equals negative 3. What can I multiply this guy by to get positive 6x? 2. So I have 6x minus 8y equals 4. We add these guys up. We add through this column, we get nothing. We add through this column, we get 1y. And we add here and we get 1. This is pretty simple. We just got y equals 1. Now I take this, I plug it back into one of these equations. I'm going to pick the first one because it's got the smallest numbers. So negative 2x plus 3y equals negative 1. And I plug this guy right in there. I get negative 2x plus 3 equals 1. I bring that 3 over. I've got negative 2x equals negative 4. So x equals 2. So my solution here is xy equals 2, 1. Okay, next question. Let's say I've got 2x plus y equals 3 and negative 4x minus 2y equals negative 6. Well, what can I multiply to get equal coefficients with opposite signs? Looks like this guy's already positive and this guy's negative, so all I have to do is multiply this by 2. Okay, that would give me 4x plus 2y equals 6. Underneath I have negative 4x minus 2y equals negative 6. I add up over here, I get 0. I add up here, I get 0, and I add up here, and I get 0. So I have 0 equals 0. This is a true statement. We have infinitely many solutions. We need to express those infinitely many solutions in a more specific way. Let's say that the question asked us to express the solution in terms of x. Last time we did it in terms of y, this time we're doing it in terms of x. Again, that means we're kind of trying to figure out what y is in terms of x. So finding y in terms of x just means solving for y. So if I have this, that means that y equals, we can bring that 2x over. So we know that our solution is xy equals, we know x can be whatever, and we know y is equal to negative 2x plus 3. So this is my answer. So this tells us all of the solutions in terms of x. Let's talk linear systems in 3 variables. So again, if we have 3 variables, we're going to have 3 equations. But don't let that overwhelm you. We're going to be able to deal with this in a very similar manner to the way we were able to deal with equations of 2 variables. So what we want to do here is eliminate one variable from 2 equations. So if we have 3 equations with 3 variables, if we eliminate the same variable from 2 of those equations, we've got 2 equations with the same 2 variables. So we have a system of 2 variables. We solve the smaller system and then we can substitute to find the 3rd variable. So this is nice because we get to use the elimination method that we just talked about. So we're going to use the same type of process there. So let's take a look at one of these. All right, let's say I'm looking at the system x minus 2y plus 3z equals 1, x plus 2y minus z equals 13, and 3x plus 2y minus 5z equals 3. What are we set up to eliminate? What would be easiest for us to eliminate? Remember, in order to use elimination, we have to have the same coefficient with opposite signs. It looks like we're set up to eliminate y here, right? If we add this equation to this equation, the y's are going to cancel here. And if we add this equation to this equation, the y's are going to cancel here. So we're set up to eliminate y. So let's do that here. So first equation, x minus 2y plus 3z equals 1, and x plus 2y minus z equals 13. We add these guys up, we get 2x plus 0 plus 2z equals 14. Can do the same thing for the last equation. We've got 3x plus 2y minus z equals, minus 5z equals 3. We add these guys together, we get 4x plus 0 minus 2z equals 4. Now we have a two-variable system. That new two-variable system is this guy and this guy. So we've got 2x plus 2z equals 14, and 4x minus 2z equals 4. Now, we can solve this system using whichever method we want. We can either use elimination or substitution. But what's up with this? What would be easier here? We're already set up to eliminate z. Already set up to eliminate z. So let's go ahead and do that. So we add this first column, we get 6x. We add this second column, we get 0, right? That's the elimination. We add this third column, we get 18. 6x equals 18 means that x is just 3. Remember, we are solving this two-variable system first. So now that we have one variable from the two-variable system, we have to find the other variable from this two-variable system. So we have to plug this into one of these. If we plug it into one of these, we'll still have two variables left, and that won't really be helping us much. So plug into two-variable equation. We can pick whichever one we want. I'll pick this one because it's got smaller x coefficient. So 2x plus 2z equals 14. We plug it in, we get 2 times 3 plus 2 times z equals 14. So we've got 6 plus 2z is 14. So 2z equals 8. So z is 4. So now we've got 3 and 4. We can plug this into one of our three variable equations and we'll have our y value. We can solve for y. I'm going to plug it into the first one. So x is 3. Let's replace that one. Let's substitute there. Minus 2y, we don't know what y is yet. And we know that z is 4. So I've got 3 minus 2y plus 12 equals 1. I bring both of these over, so I'm subtracting 1 minus 3, so negative 2, minus 12, so negative 14. I have negative 2y equals negative 14, so y is 7. The answer to this three-variable system is x, which is 3, y, which is 7, and z, which is 4. All right, let's look at this one here in the lab manual. So which variable here makes sense for us to eliminate? We've already got one variable eliminated from this last one. It's y, right? Y is eliminated from the last one. So let's just eliminate y from these up here. So if I've got positive 1 coefficient for both, I just need to multiply one of them by negative 1 and we're good to go. So I'm going to just choose this second one just because. So I've got 2x plus y minus z equals negative 8. This second equation is going to become x minus y minus z equals negative 3. I add, I get 3x plus 0 minus 2z equals negative 11. Now I've got my new system of two equations, right? The first one being this guy, so negative 2x plus 4z equals 18, and my second one being 3x minus 2z equals negative 11. Which of these variables would be easier for us to eliminate? Probably not these, right? Because 2 and 3, as we saw earlier, we would have to multiply both equations by something, which is more work than we need to do. Because, right, if we just multiply this second equation by 2, we'll have positive 4z and negative 4z. So let's just multiply this guy by 2. So we've got negative 2x plus 4z equals 18. We've got 6x minus 4z equals negative 22. We add these together, we get 4x plus 0 equals negative 4. So x is negative 1. We can go ahead and plug this into one of our equations of two variables. So I'm going to plug it into this one. So I get 4z equals 16, so z is 4. So I've got x equals negative 1, z equals 4. I've got 2 out of my 3 variables. So let's use these guys in one of our 3 variable equations and find y. So I'm going to use this one. So negative x plus y plus z equals 3. We want this guy to come in here. We want this guy to come in here. We've got negative 1 plus y plus 4 equals 3. Negative 1 is just positive 1, so we've got y. Positive 1, positive 4 is 5 equals 3. So y is negative 2. So my full answer is x, y, z equals negative 1, negative 2, and 4. All right, let's do one like this. So example, let's say we've got x plus z is 5. We've got y plus z is 7. And we've got x plus y is 0. All of these equations have 2 variables, but we don't have 2 equations with the same 2 variables. So we don't have a 2-variable system. So what can we do here? Well, let's just keep trying and see what happens. So normally we know that we want to try and eliminate one variable in multiple equations. So we know we're missing the y in this first one. So let's eliminate the y in one of these guys. So let's try eliminating y. So we've got y plus z equals 7. Let's multiply this second equation by -1, so we have the same coefficients with opposite values. So negative x minus y equals, well, -0 is just 0 still. Let's add these together. Looks like we've got negative x plus 0 plus z equals 7. So we got rid of the y, but we gained a z, which is okay, right? Now we have this equation with two variables, x and z, and this equation with two variables, x and z. So we gather those together. We gather this one as well. And we solve this guy. What solution method should we use? Well, we've got positive x and negative x here. Seems like it lends itself pretty well to elimination. So let's add these guys together. We get 2z equals 12. So z is 6. All right, let's plug 6 back into one of these two variable equations. X plus z equals 5. So, but we know that z is 6, so x plus 6 equals 5. So x is -1. Now that we know -1, now we can plug either of these into one of the equations that has y to find y, and they should both give us the same thing. We only need to do one though. Let's use z again. So we know that y plus z is 7, and again we know that z is 6, so we know that y is +1. So the solution here is x, y, z equals -1, +1, and 6. Let's say we have something like this. So we've got x eliminated in this first one. Let's just eliminate x over here. We've already got opposite signs. Let's try and eliminate x here. I already have opposite signs. How can we make this -2x? Well, we just have to multiply by 2. So I've got 2x plus 3y equals 2. And I've got -2x minus 4y plus 2z equals -2. So I end up with 0x minus y plus 2z equals 0. All right, let's write our new system of two variables. So my first equation was y minus 2z equals 0. My second equation is -y plus 2z equals 0. If I add these together, we're already set up for elimination. If I add these together, I get 0, 0, and 0. This is another one of those infinitely many solutions situations, right? So we have to figure out what these solutions look like in terms of something. question that's like this in WebAssign, it asks for you to express it in terms of z, so that's what we'll do here. So we need to find everything in terms of z. That means z is going to be itself. We need to find y in terms of z, so we need to solve this equation in terms of z. So y, so that just means y equals 2z, simple as that. Now we just plug in this to our one and only 3 variable equation. I guess we could also use this 2 variable equation. Either way, doesn't matter. We have negative x minus 2y plus z equals negative 1. We don't know what x is, but we do know that y in terms of z is just 2z plus, and we know that z is itself, and all of that equals negative 1. So we have negative x minus 4z plus z equals negative 1. So negative x minus 3z equals negative 1. Negative x equals negative 1 plus 3z. And I'm running out of space here. This means let's divide everything by negative 1. So we have x equals 1 minus 3z. So this is x in terms of z. So we have x in terms of z, y in terms of z, and then of course z is in terms of z. So our answer is x, y, z equals x in terms of z, so 1 minus 3z, y in terms of z, so 2z, and z in terms of z, which is just z. That's my answer. Alright guys, that's all I have for systems of equations. Hopefully everything is making sense, and I will see y'all next time for applications of this stuff.